Let's take a look at another example that has just a little bit more meat to it here. I'm going to have a vector field in two space given by f of r equals negative yi plus xj. Now I started out this table so I can kind of think about what's going on here. Let's look at the magnitude for each of these. When I'm at the point -1, go ahead and set up an axis here. When I'm at x is -1, y is -1, so here's -1, -1. When I'm right here, this is going to be my vector. Now, what's the magnitude of this vector? Well, the magnitude of I minus j is going to be the square root of 1 squared plus -1 squared. That's going to be root 2. Now, I is 1 in the positive direction, j is 1 in the negative direction. So this vector is going to look like this. When I'm at -1, when x is -1, y is 0. So when x is -1, y is 0, I'm right here. This has no x component, but the y component is a -1, so it's going to be like this. When x is -1 and y is +1, so right here is going to be my initial vector. Well, if I'm thinking of this as r. Now, I'm going to go 1 in the negative direction for x and 1 in the negative direction for y. So I'm going to be down here, essentially at -2. So that's what my vector is going to look like. Now, I'm going to finish up this table real quickly here. And actually, I'm going to add to this magnitude. This is going to have a magnitude of root 2. This is going to have a magnitude of 1. This is going to have a magnitude of root 2. Now, if I work on this table, this is going to be I plus 0j. It's going to have a magnitude of 1. This is just going to be the 0 vector, obviously with a magnitude of 0. This is going to be a negative I plus 0j. It's going to have a magnitude of 1. This is going to be I plus j, which will give me a magnitude of root 2. This would be 0i plus j, which is going to give me a magnitude of 1. And this is going to be negative I plus j, which will give me a magnitude of root 2. So let's go ahead and work on the second row. When x is 0 and y is -1, so I'm right here. That's where I'm going to start off at. This has a vector that is a +1 in the x direction. So it's going to look like this. 0, 0, there's nothing. There's nothing there. When x is 0 and y is +1, I'm right here. And this is going to have a vector that is -1 in the x direction and no change in the y direction. So it's going to come over like this. Now down here on this one, when x is 1 and y is -1, so when x is 1, y is -1, so I'm right here. I'm going to be +1 in the x direction, +1 in the y direction. So that's going to be up 1 over 1. That's going to go here. Of course, that magnitude is root 2. Now, when I'm at x is 1, y is 0, so right here, this is not going to change in the x direction, but the y direction is going to be a +j, so that's going to bring me to there. And this last one, when x is 1, y is 1, so I'm right here at this point. I'm going to be a -1 in the x direction and a +1 in the y direction. So I'm going to come up here to 2. And that's what this vector field looks like. Or in general, there's a few members of this vector field. Now I'm going to go ahead and erase this one vector I put in there because it kind of clogged things up a little bit. There we go. Now, when I'm looking at this, I want to think about this for a second. If I start replacing, I just erased that one vector. If I start coming out here and saying, hey, what if I start drawing vectors out that have length 1? There's a length 1. Here's a length 1. Here's a length 1. Here's a length 1. What it appears is that every one of these vectors are orthogonal. That's what it appears to be. What happens now if I take a look at all the vectors that have length 2? Well, here's R coming out here. This has length 2. This one has length 2. This one has length 2. And this one has length 2. What this appears to be is concentric circles. It looks like I've got this circular thing going on here. And all of these vectors are orthogonal to the circle. Well, let's think in general about the magnitude of f. The magnitude of f is going to be the square root of negative y squared plus x squared, which equals the square root of x squared plus y squared, which is the square root of r squared, which is r. So what's happening is these vectors are the same length as the radius. Now I'm suggesting here that these are all orthogonal, at least they appear to be orthogonal. Well, we can check real quick, because the vector r is equal to simply xy, and the vector f is equal to negative yx. So let's look at the dot product. If I take r dot f, I'll get x times a negative y plus y times x, which is definitely 0. Therefore, these are in fact orthogonal, because the only way a dot product can be 0 is if the two vectors are orthogonal to each other. So our vector field really is a set of concentric circles getting bigger and bigger and bigger, where the vectors are actually tangent to the circle.